Hello, this video is to show how to use STAAD.Pro to model braced frame in a building, and we will use the same example for wind load and seismic load calculation in class. And this slide shows the gravity load on this building. And this is the floor framing plan, shows the beam spacing and the location of the braces. And in the X direction, we have 4 braces and marked with the blue color. And in the Y direction, we have 6 braces and marked with red color. And in today's example, we will model a typical X direction brace and a typical Y direction brace. And this is the elevation in the X direction. And this is elevation in the Y direction. And we will model the brace in the X direction first. And in order to let the program run, we have to assign the section properties instead. But before we design the structure, we don't know the member size yet. But we can do a rough estimation and pre-select the member size in order to let the program run. And for this example, I pre-select the column size W12 by 79 and select the beam size W18 by 46 and the roof beam W18 by 35. And the braces, I just pre-select double angle 6 by 6 by 1/2. And those member is just a rough estimation. After we do the analysis and design our member, and we can refine our model later. And in the X direction, and we have to assign the load. And for each type of load, we just do the service load. Service load is unfactored. And after we input each load, and we can do the load combination. And based on the tributary area, and we can calculate the dead load on each beam. Snow load on the roof, live load on each floor, and we calculate wind load in class on each frame, and we also calculate seismic load on each frame. And in the Y direction, we also need to pre-select the member in order to let the program run. So based on the rough estimation, I have the column size 12 by 79, have the girder size W21 by 83, and the roof girder W21 by 44. And the cross bracing, I use double angle 6 by 6 by 1/2. Again, those member size is just a rough estimation. After I do analysis and design the member, I can replace those with the accurate member size. And in the Y direction, that's the girder direction, subject to the point load. Those point loads spaced at beam spacing, and this is the dead load. And this is snow load. Those point load are the beam reactions. The live load on each floor. The wind load based on our class example. And the seismic load also based on our class example. After we input each service load case, and we can do the load combination using ASCE7 IRRFD load combination. There are 7 of those, and we need input all 7 load combinations and do the envelope to identify the governing design load on the brace members. Okay, so now we begin with the X direction braces. Okay. Now open the STAAD.Pro software, and first thing to do is configure. In order to select the unit system, we have the English unit system, and click OK. After that, do a new model, and file name, I just called X direction brace, and then select a folder to save the file. Check the type, Analytical, and double-check unit system is English, then go to job information. And this job name is Brace Design X direction class example. And client, I just put RIT, and job number, and put the course number. And the reference is the wind load and seismic load class examples. And put your name, enter the date, and comment. X direction brace and we need to identify the governing design load. Then we create a new model. And this guides us to the Analytical Modeling window. And before we do the input of geometry, and we need to double check the unit. And for the unit, input unit currently set as cube feet. Okay. And in order to double check, we use this input unit. Then under English, we select foot and kilopound apply. Then we can input, okay, we can input the coordinate of the frame. And since the frame is a 2D structure, it's easier for us just see the XY plane. So I just do this view and select the front view button. So after that, I will input the coordinate of the frame. Okay, so first I will input 4 nodes here, 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 and here. Okay, so we just input those 4 nodes. 0, 0, 0, and I put 30, 0, 0, then do 0, 18, and 30, 18. Okay, So after that, we go back to this geometry and use Add Beam button. Connect the nodes and escape. And since we have multiple members, it's easier for us to show the node number and the beam number. So I just right-click and labels, turn on the node point, node numbers, and beam numbers, and click OK. So after that, I select this member 3 and use translational repeat. And then global Y direction, I do 2 steps and default spacing 15. And after that, I select its link steps in order to create the column member, and then do OK. And after that, I need to create a middle point for the beam. So I highlight member 3 and then use insert node and add midpoint. Click OK. Again, do the same thing for member 6. And then do member 9. After that, I use this Add Beam button to draw the diagonal members. And now done with geometry. Just escape. Serial model frequently. And now we're done with geometry and go to the tab to the right, Properties. Since we don't know the member yet before we do the design, but we need to pre-select the member size. So just do a rough estimation. I pre-select the member size right here. So instead, I use section database. Then select the beam. (18 by 46). Then select the beam 18 by 35 and the column 12 by 79. And then do the angle. Select the angle. Then we select this double angle option. Use long leg back to back. And then from the list, select 6 by 6 by 1/2. So we have 6 by 6 and 8 is 8/16. So it's a ½ inch thick. After that, close. Then we will assign this beam 18 by 46 to the floor beam members. Use cursor to assign and assign to all the floor beams. And escape, then do the 18 by 35 and assign to the roof beams. Escape, then select the column 12 by 79, assign to the column members. Escape. Then we do the double angle and assign to all the diagonal members. Then escape. After that, every member shown on the screen has a section property, and go to the right material. And since we assigned the hot rolled steel shape, so it's automatically carry the steel material to the material tab. We just accept it. If it doesn't carry automatically, we can do the steel and then assign to view. Okay. Done with the material and go to specification. And for specification is the place that we want to release the moment at a hinge connection and also assign the brace members to a truss member. And so first, we want to release the moment at hinge connection. So we use the beam option and the location. Do the start and release MZ for the pinned connection and do add. And then do the beam again. Select the location and release MZ and do add. Then hit the beam again and select the truss option and add. Okay, so for those specifications, now we need to assign to the right member. And we know that for brace the frame, the beam to column connections are all pinned. So we can do the start MZ, use cursor to assign, and escape. And then do the end MZ, use cursor to assign. Okay. And after that, we need to also release the end moment at the top of the column and escape. Now done with all those member release. And after that, we do the member truss and assign this to all those truss members. For the braces, the diagonal members, those are truss members only subject to the axial load. And escape. So now we're done with the specifications. And go to the support. We will use the pinned support. The column to foundation connection is pinned. So we will use pinned support. Then assign the pinned support to the bottom of the column and escape. Okay, so done with support, then we go to the loading. And for loading, we need to assign all those load cases, including dead load, live load, snow load, wind load, and seismic load. So first, do load case details and add. First load case is the dead load. Then we assign a live load case. The third case, snow load. Then do the wind load. And the seismic. Okay, so after we define all those load cases, and now we need to do load combination. We need to define load combination as well. So we define the load combination. And for load combination, we need to refer to the ASC 7 load combination right here. Okay, so we will define all 7 combinations. Combo 1, I have that load case, and load factor is 1.4. Add. Then do the combo 2. Have a dead load 1.2 plus live load 1.6. Then we have snow load. Load factor is 0.5. Add. Then we do the load combo 3. Dead load 1.2 and live load 1.0. Snow load 1.6. And do add. Then we have a combo 4. Dead load 1.2 and wind load 1.0. Live load 1.0 and snow load 0.5. Do add. Combo 5. Dead load 1.2 and the live load 1. Seismic load 1, and snow load 0.2. And add. Then we define combo 6 has dead load 0.9 and wind load 1.0. Add. And the last combo, combo 7, dead load 0.9 and seismic load 1, and to add. So now we defined all those load combinations and close. And after that, we need to let the program to find the maximum load using load envelopes. So highlight the load envelopes and do add. Then I do the envelope 1, type select strength. Then adjust from combo 1 to combo 7. And let the program to find the maximum from the 7 load combinations and to add. Close. Okay, so now we defined all the load cases and the load combinations. And next step, we need to add load items for each load case. So we start with dead load. Highlight dead load and do add. And for dead load, we use member load. Just refer to the load diagram. Okay. So for this dead load case, we have the member force uniform load on the roof beam, on the floor beam. Okay. So we will use member force, uniform force, and the magnitude for the dead load is on the roof negative 0.078. Okay. And direction, global Y direction. And since the member load occupied the entire member, we just leave D1, D2, and D3 as 0. Okay. Then to add. And then we do the floor dead load, negative 0.955, global Y direction, and do add. Okay, and then close. We can assign this roof dead load, use cursor to assign to roof beams. And escape. And then assign this floor dead load, use cursor to assign to the floor beams, and escape. Then we need to add load item under the live load and highlight this live load case and do add. And take a look at the live load. And live load is on the floor 2 and floor 3. Member load and use uniform force -0.313 kips. And in the global y direction, leave D1, D2, D3 at 0 and do add. And close. Then we assign this live load to second floor beams and third floor beams. And escape. Done with live load. Then we go to snow load and add. And snow load is a member force. Okay, member load use uniform force. And for snow load case, we have snow load on the roof, 0.094. Negative means downward. And do add. Then we close. And then assign this uniform force on the roof beam. Escape. Then highlight the wind load case and do add. And the wind load are nodal load. Okay. And in the X direction, we select nodal load and node option and take a look at the wind load case. And we will input the nodal load on each story level. In the X direction, we have 6.9 and do add. And we have 13.8. And 15.2. And close. After that, we can assign this the nodal load on each story level. And escape. And then check this seismic load and do add. Again, nodal load in the X direction and take a look at the seismic load case. We'll input those nodal load. And we have 16.2. 23.3 and 13.3. Close. Then assign those loads to each node. Then escape. Then highlight 13.3. Use cursor to assign to the second story level and escape. Okay. So now we're done with the load assignment. Save your model and we're done with loading. Okay, in loading, we need to define load case, load combination, envelope, as well as assign each load items. And after that, we go to analysis. And from this analysis window, define command and just select this no print and add. Then close. After that, you should see this perform analysis command in the analysis window. And then we define the output, use this post-analysis command. Then we define command. The purpose of this example is to figure out the maximum force in the brace members. So I will use the maximum force, choose maximum force, and do add, and close. Then from this list, you see the bottom here, print maximum force envelope, and the question mark means that you need to tell the program that which members you want to output. So I highlight the print maximum force envelope and use cursor to assign to all the brace members, and escape. And now I'm done with the modeling procedure. Save my model again and hit this run analysis button. So after that, we target at 0 errors and just ignore the warnings. And then we go to the view output file. And just double click the maximum force envelope list. And we can identify, okay? And this Fx right here is give you the maximum axial load in the brace members. And we can find that in this X direction brace, the maximum compression is 58.81 kips in compression right here. And this is the maximum. Okay, so this is the maximum compression. And you can print this output file to a PDF file. And now you can see that you can print the output file and then highlight the maximum force that governs the design. And you will use this maximum compression force as well as the length of the member to design the braces. Okay, so identify the maximum. And let's take a look at the member 14 location. And is this member governs your design. Okay. So now we're done with the X direction braces. And so next we want to model. Okay, so we want to model the Y direction. Okay. And let's take a look at the Y direction. And the Y direction braces is a cross bracing, and dimension is the girder length 25 feet, and the girder subject to the beam reactions, so the load on the girder lines are the point loads. Okay, and then we do the load combination, similar procedure as the X direction. just repeat, okay? Open the software. Configure, select English unit, and leave everything default, and click OK. A new model. And this I call the Y direction brace. Okay. And then do the select a folder that save the files. Check the type analytical and unit is English. Then go to job information. And this is the brace design. In Y direction. And clients put RIT, job number, course number. And the reference is the class example, wind load, and seismic load. Put the name and select the date. The comment is to identify the governing force. In the braces of Y direction, then we create a model. Again, before we do the input, double check the input unit, and we can do the input unit button, enter English, and length use foot, and force use kilopound, and apply. After that, I change the view to front view, and I go back to geometry. Then I input the nodes. So I use 0, 0, 0, and 25, 0, 0. Then do the 0, 18, 0, and 25, 18, 0. Okay. After that, I use turn on, use right click, and select labels and check node number, node point, and beam numbers, and click OK. Then I use add beam button to connect the nodes 1 to 3 and 2 to 4, then 3 to 4, and then escape. After that, I highlight this member 3, okay, so highlight member 3 and use this translational repeat button, and then do the global Y direction. I do this 2 steps, and each step is 15 feet. Use link steps to create the column members, and click OK. Okay. So after that, I use Add Beam button again to draw the diagonal members. Okay, and escape. Done with geometry. And for the properties, and a rough estimate the member size in order to do the analysis. So after I get the accurate force and do the accurate design, I can go back and refine my model, use the correct section properties. So currently, I just pre-select the section. The pre-select size is right here. I will use W21 by 83 for the girders and W21 by 44 for roof girder, W12 by 79 for the columns, and for diagonals, use double angle 6 by 6 by 1/2. So first select W21 by 83. Then select W21 by 44, W12 by 79, then select the angle and use double angle option, the long leg connect, and then go down the list and select 6 by 6 by 1/2. By 1/2 use 8. This 8 means 8/16 of inch. So do the add and close. Then we assign the girder, floor girders, W21 by 83 to the floor girders, and escape W21 by 44 to roof girders, and escape. Then select the column 12 by 79 to all column members, and escape. And the last is the double angles assigned to all those okay. So down with properties and go to the materials. Okay, so it's automatically carry the steel materials, which is accepted, and go to specifications. And for specifications, we need to release the moment at the hinge connection or pin connection. Also assign the truss members to those diagonal brace members. So first do the beam, start, release MZ, and add. Then do the beam again, location end, release MZ, and add. And then do the beam again, select the truss option, and to add. Then assign the start MZ to those beam members, and escape. Then do the end MZ and assign to the beam members again, as well as the end of the column. Okay, escape. And then we do the member truss. Okay. So then we assign those diagonals and member truss. And after that, we're done with specifications and go to support. And again, a pin support, create, pin support, do add, and then assign the pin support to the bottom of the columns and escape. And done with support and go to loading. And for loading, we need to define the load case. Okay? So highlight the load case details and do add. And we will do that load case and do add. And second one is live load. Then do the snow load case. And then do the wind. The last is seismic. Okay. So that's the load case, 5 load case. After that, we need to define the combinations, load combinations. Use ASCE7 LRFD load combination. So I just do the combination, combo 1. And for that load factor is 1.4. And add. Okay, you can see the combo 1. Okay, and then we do the combo 2. Use that load factor is 1.2. The live load is 1.6. Okay, and after that we have a 0.5 snow load. Then to add combo 3. And we have that load 1.2. Live load 1.0. Have snow load 1.6. And do add. Combo 4. That load 1.2. Wind load 1.0. And we have live load 1.0 and snow load 0.5. And do add. Combo 5. That load 1.2. Seismic load 1.0. Live load 1.0 and snow load 0.2. Add combo 6. Dead load 0.9. Wind load 1.0. Add combo 7. Dead load 0.9 and seismic load 1.0 and add. So we're done with all the 7 load combinations and close. Next, we will do the load envelopes in order to identify the maximum force for all those 7 combos. So highlight load envelope and do add. And we define envelope and type. I make this strength limit. And then put all 7 combos to the right. Okay, and just to add. Close, and you should see this envelope. Okay, so now we're done with all those definition, and now we need to put the load items under each load case and highlight the dead load. And based on the dead load diagram, let's take a look at those. Those are the point load. So and first we'll use nodal load, and the y direction is negative 4.7. Negative means downward direction, so just add. Don't close this window and change that to negative 5.2. Add. And house negative 14.1. Add. And negative 15.5. After that, we'll use the member load option, concentrate the force, and put P, negative 4.7, and global Y direction, D1 is the dimension from the point load to the member start. That's the D1 dimension. So for the first one is 6.25, which is the beam spacing. And the second one is 12.5 to the member start. And third one is 18.75. Then we will change that to 14.1, negative 14.1, and D1 is 6.25, 12.5, and 18.75. That's based on the beam spacing. Okay, so now close. Then we need to assign each load item. First, the nodal load. Okay. Escape. 5.2 assigned to. 14.1 assigned to node 5. Node 3. Escape. 15.5 assigned to second floor, third floor. Escape. Then we assign this 4.7, 6.25 from the member start. Escape. The second one. Escape. And 18.75. Escape. Then go to the 14.1. Escape. And do the 12.5. Okay. Then the last one. Assigned to the second and third floor. Okay. Escape. So we're done with the dead load assignment. And go down to the live load. Okay. And for live load case, the port load on the second and third floor. And we will define this 18.8 and 20.6 as node load, and those 18.8 as the member concentrated force. Okay. Add node load for the y direction negative 18.8. And negative 20.6. Okay, and go to member load. We have the concentrated force. The magnitude is negative 18.8 in the global y direction, and D1 6.25. That's the beam spacing. Change it to 12.5 and 18.75. Close. Then we can assign the node load. Escape, then assign the concentrated force. Okay, so this done with the live load case. And then do the snow load. And the first snow load is on the roof. First node load, I have the X for the Y direction has the negative 5.6. And the negative 6.2. Then do the member load, concentrated force, magnitude negative 5.6, D1 6.25, GY direction, then change D1 to 12.5, add, and then do 18.75 and add, close. Then we need to assign the load to the roof, okay? So just then do the concentrated force. Okay, done with the snow load assignment. And then go down to the wind load and add the nodal load in the X direction, and based on the load case. Okay, so we'll input those nodal load. $10.6 in the X direction. Okay. And the second one is 21.2. And 23.4. Close. Then we assign the nodal load to each story level. And escape. And the last case is seismic. Okay, so highlight seismic and add. Again, is node load in the x direction. And we need to refer to the load diagram. And this is the load that we will input. It's 10.8. And 15.5. 8.9. And close. Then assign those. Okay, so done with all those load definition and assignment. And so I save my model and go to analysis. And for analysis window, define command, choose no print and add. Okay, so you should see this. You should see the perform analysis command. And then we will do the post analysis command to input, to identify the output. So go to post analysis command and define command. And again, we will target at maximum force in the diagonal members, the brace members. So use maximum force and do add. Then close. And from the list, print maximum force envelope and we assign to, okay, assign to select. Okay, assign to those brace members. And then save my model again and run analysis. Okay, 0 errors. Ignore the warnings and go to a view output file. Okay, so maximum force envelope. Then we can identify the governing design force. So from the output, this Fx, which is axial load, we identify the maximum as 62.59 in compression. C is in compression. So let's take a look at the member. That's the member 11. And 11 is right here. Okay. This is the member 11, which has the member 11 and has the governing compression, which is 62.59 caps. Okay, so now we are done with our the example.